wrong figures but that was the publisher, but it was still my fault. Okay, guys, we're looking at back into chapter 11, and we talked about the different files, right? And we added the long file, which is available. No, it's not on this yeah, the long file, long word file, which is supported by the MicroLogic 1000. I imagine it's supported by all the PLCs after the 11,000. Then we looked at the, everybody okay on our compare instructions? Okay.
More or less. Do you mean the
greater than, equal to, not equal to? This falls back into math. And this is what's nice about a PLC. We can't, it's hard for us to do this with relay logic. But this is not a relay, right? This is a computer. So what we do is we get all these instructions, or most of the instructions that's available for a computer and a high-level programming. These are addressing modes. We'll deal into these. So the ones that we've been using so far is immediate and direct. Everybody okay on those addressing modes? So immediate is where we deal with constants, right? Understand? So that means the actual operand is part of the instruction itself. Direction means we give the direction to where the operand is located at. So this is when we specify one of our registers. That would be direct address. And then we'll deal a little more into indirect addressing. And we have another addressing mode that's called indexed addressing, which we'll talk about later on. And then we added the textbook doesn't talk about, since we use this so often, or something similar to it, since we use this so often, what this does is this gives us the ability to see when two operands are within a range, right? So we have the ability to set ranges. Since we do that so often, it makes sense that the PLC would add one instruction that would let us do that, right? Y'all understand that? Yes or no? Yeah, so what does this right here give us to? Greater than, and then we feed that into a less than. What does this give us right here? It makes this run true through a range. So this run will be true when counter 5 accumulator is between between what? 6 and 9. So it's true between a range, right? You understand? Okay, because this is greater than.
or equal to, isn't it?
Okay, so you're right into it. So this is greater than equal to, so that's equal to 2.
So it would be 5
5 to 10.
to 10.
This run will be true between that range. And we do that all the time. You know, we're seeing, okay, between this range is good, inside of this range is bad. Right? Y'all understand that?
That's just counting up. Then when it gets between that range, it turns on.
Yeah, this output 2/0. That between a range. And this, and what we find out, if you keep doing the same thing over and over and over again, then sooner or later they're going to add one instruction that does that, right, for it.
So then, if I may, when it reaches run 2 there, force B becomes 10. Then
Now this only looks for 10, so this run's only true for one count. This run is true anything above 10, right? If it's greater than 10, then this run right here would be what? Right? You understand? So what this does is it gives us the ability to set up, and I know y'all was looking at cascading timers and stuff like that, Well, instead of cascading timers, have one timer start another timer, and using this, we could do what? We could do it all with one timer and have the timer set for the range, and then make each run either valid between the range or after at a range, right? You understand that? So what it does, it would actually say runs. And I think I got a problem. So this is
Would you go back to that when you're done and just show just the run of it for me?
now what we'll do is we'll actually run a program that actually runs some devices. So we could talk about this all day long, but until we run motors, we see motors run and lights come on. You know, we're a visual type species. So what that means is if we can actually see it instead of talking about it, then it makes a lot more sense to us. So what I'm gonna do is I'm gonna connect up to my MicroLogic, and I'm gonna wire up my inputs and my outputs, and then we'll actually run the program. So the program that we'll be looking at will be here, ParseLogic 1100. I don't have it for my, or did I make it for them? No, I don't think I have it for the 1100. I think I have it for the 1000. This doesn't have any comments. I'm trying to get used to putting a comment. So I have a master start stop station, right? But first thing we'll have to do is wire my inputs and wire my outputs. The way we have this PLC hooked up is we have it hooked up for syncing. And the way the Allen Bradley PLCs work is they allow you to decide whether you're going to sync or source your inputs. But they do it in groups because so what I have, if we look across the top here, if I can get my camera in here, I'm supposed to be. Yeah, well, it don't show up here. But yeah, it's recorded. No, it don't show up on the video. See, but it did. So this PLC has two commons. It's got a DC common here. Has a DC common here. It has a DC common here. And then it has a DC common here. Now this guy has its own DC power supply, a minus and a plus. These DC power supplies that are inside the PLC are only intended for input. You don't run outputs on these things. You run what? Input. And then what you need to do is you need to figure out, okay, is this within the range of how much current these inputs can handle? So the more solid state inputs that you have to run, these guys have to be powered up, right? You understand? You could run thousands of switches off that power supply because a switch or a contact requires no current. But as soon as you hook up a solid state relay, those guys most of the time have to be what? They have to be powered. They take 3 wires. So what we do is we usually run those off an external power supply. So you can see here's the minus and plus outputs, and I'm not using them. So what I'm doing is I'm running my common up from the power supply that's built into this unit down here. It's a nice big power supply. You know, so I'm bringing the minus right here. So this is the minus. This is the minus. So what I'm doing is I'm configuring my inputs to be syncing, right? You understand? So my actual input devices will have to be what? Sourcing. Does that make sense? So what I would do when I wire this thing up, and they bring the power supply out to us. Well, they bring the power supply out to us. Here's the power supply. And so Germans like to use red for positive and blue for negative. Over here, you can use red for positive and black for negative. But I've noticed that they like blue. Okay? So this would be my negative power supply, and this would be my positive power supply. So what that means is if I'm going to hook up my input for sourcing, then what am I going to have to do? Well, what I'll do is I'll take this, I'll take the positive output of my power supply, and then I'll hook it to a common of all my switches. What I'm going to do is I'm going to take the positive output of my power supply. Sorry. My feet is tangled up and everything.
All right.
I think I made it. So I'm going to take this positive output of my power supply, and then I'm going to run it to all my switches. Now, the way my boxes are set up is these are the two. This actually is wired directly up to this push button, this push button, this push button, this push button. And then on this side, I have switches. This is an inductive sensor, and this is a potentiometer that I could use for an analog, to simulate an analog sensor. So what I'm going to do is I'm going to come over here and take the positive output of my power supply, and then what I'll do is I'll just bring it over here. The best way to put it. And I'm going to run it to that common. Now every input device, I'll just come over here, and I'm going to come over here and just jump them. I'll see what I'm doing. And so what I'm doing is I'm setting up a common for my input devices. So I'm running a positive common over here because my inputs are set up for what? Negative. So they're using a negative common, and over here on my input devices, I'm using a what? A positive common. Yeah. So you can see all I'm doing is taking the jumper wires here and just jump the commons or the black, but it don't make any difference. It's just that you would have to keep it. So I could use the reds just as well on the switch of the common, right? You understand that? It's just I'm gonna have to be consistent down through my line. And then once I've got all these things set up, depending on how many I need. You see, that's all I'm doing. I'm just doing what? Okay, so what I've done is I've set up a common for my input, my actual switches, and I'm using a positive common for my switches, and I'm using a negative common for the PLC. So my PLC input is set up to what? Sync, and my switches are set up to source. Now my outputs, if I can get my camera up here, what I've done on my outputs is I'm bringing, don't pay any attention, this is the only color wire I had. And so this is the positive on my outputs. And then what I've got on this one, the way this is set up, this is a relay output, and it gives me the ability to hook up DC, I can hook up AC, I can do anything I want to. But what I have right here, this says a common. And then I've got this jump to all the commons. So what I have is I have the positive of my power supply hooked off to the common on my outputs, right? You understand? So I've set my outputs up to do what? Source. And then that means I'm going to set my output ports to source. So my output devices, I'll set them up to what? Sync. That makes sense? So what I would do on that box is what? So here's my output box right here. It's got motors and got lights. And I've also set up a reversing circuit. So what I would do on this is what? Yeah, I would come over here and take this and hook this up to what? Minus. I'll hook this up to my minus, right? You understand? And then I'll come up here to the common on my motors. There's two of them right now. And then I would take my outputs, which are set up to source. See what I'm doing? I'm over here. Okay, so what I've done is I brought the minus over here, and I have that jumped over here. So I've set up these as syncing, right? And my outputs are set up to do what? Source. Makes sense? Everybody okay so far? And then these outputs over here are designed to source, so I can just come over here and hook this up. Now, if you were wiring directly to the PLC, you would be wiring these up here, right? You understand? So you would be wiring these individual inputs right here, but these wires, as I can show you that. So these wires right here just go where? Down to the banana plug jacks right down here. Well, that's not quite true, but technically that would be the way it would work. Okay? That's the way you wire it. So some PLCs are set up strictly, so if I was to look at the 1200, you have no option here. So on the 1200s that we have, the DC, 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 the inputs are set up as syncing, the outputs are set up as sourcing, but you still have a common. Now, why they do that is that so you can run these devices off an external power supply. You don't have to run them on the power supply that's part of the PLC, right? You understand? Because that little old tiny PLC can't control or can't provide a lot of what? Of current, right? Or power. You don't understand that? So what we would do instead of jumping the power supply here, so I could have took the minus here and jumped it from there to there, and then those input, then I would have had to take this positive and I would have to run that out to my devices, right? You understand? Yes or no? That makes sense? Yeah. So we have this hooked up, and I'll have a diagram in a minute. So this PLC is an AC DC relay. So it runs off AC. So that's why we have a 120 volt power cord coming into it. So they're labeled L1, L2, and ground. You need to run a ground for these things. And then it's got an internal 24 volt supply that comes up to here. And then the analog inputs, which are right here, these run off 10 volts. So you can't use this power supply to run these analog devices. So you'll definitely have to have an external power supply to run those or do some tricky stuff. Are we okay? So that's the way we wire these things up. So it's not that once you understand one, so I can't find the wiring diagram for the 1200 PLCs. I've looked all over that so I could show you that, but I don't need it, right? Understand? Because they do what? The same. Except on the Siemens PLCs, the minus they label as M. And then the positive they label as L, plus L. That's the only difference. So once you figure that out, so the inputs have an M, and you can either use the internal power supply, right, or you can use a what? External power supply. And then the outputs, you don't power the outputs off. You never, or try to never, power the outputs off that little internal power supply, right? You understand? So normally you will always have. No, I'm going to say you can, as long as you don't exceed the ratings of the what? The power supply, internal power supply. But they recommend that you don't run the outputs off the internal power supply, that you actually have an external power supply for that. That makes sense? Everybody okay? So what's the first thing I need to do if I've just hooked up the PLC? I ain't hooked it up yet. So what's the next thing I need to do? Yeah, I need to establish communication with the PLC. And this is true every time, guys. Every time you switch over to a different PLC, you have to establish communication with that PLC. A lot of times now it's built into the package. So if you load it into TIA software for the new TIA software that Siemens does, it pops up with a window, and the first thing you would do would try to go online. And when you try to go online, that will automatically do what? Yeah, figure out what you got out there if you've already got the driver installed. But for RS Logix, we have to run RS Links, right? Or 500. Like I said, I'm not familiar right now with the 5000 because we just don't have enough PLCs for me to spend a lot of time on that. And then I go to what? Communication, then I go to configure driver, and then we're going to be using the DFI input, and I'll just go to configure, and then I'll auto configure, and hopefully. It's always helps.
What did you say you did to make it? You don't have to go through this. You just do
Sometimes what you can do, if you're doing the same thing, you can bring up RS Logic and just tell it to go online. What you do in RS Logix, you just go and say who's active. So what I would do is I would come up here in RS Logix, and at the very top, 500, and at the very top of the screen, right here it says comms, and I say who's online, and I go up here and click that. And if it comes up here and says, hey, I'm online, then we're okay. It says this guy's not online because I was using the Ethernet input last time I talked with him. So right now we're up here on DFI, so I'll go up here and see if anybody's active on the DFI input, which would be this guy, and see he hadn't found anybody yet. Okay, but he's looking. You see him, a little flashing little thing right there. Oh, he was. Yeah, he's looking for it. But in Dali, there's something a little bit different, and hopefully this works. Because I'm already spending too much time. Okay, here we go. RS Links. This guy right here. Configure. Let's see if we can find it. Okay, so found it, right? Once you got it plugged in. Most of the time, by the way, but if it don't work, and it says they can't find anything at the COM port that is configured to, then you have several COM ports you can look at. But on what we can do is go over here and let's do it differently. I'd have to figure out how you can go through control panel, or you can go through my computer, and then you can go to properties. Then what you want to do is go to device manager. And then what you do is down here. So this is the list of everything that this guy supports.
You don't hide what's hidden there.
Yeah, but we don't need to unhide anything. Because right here, this is COM ports. And what I would do is I would go out there and figure out which COM port is assigned to this device. Now this has got several software COM ports on some Bluetooth devices. I know this is not Bluetooth, so I would use this one. Another thing I could do is I could unplug it and see which one disappears, and then plug it back in, and then it would reassign it. And this would tell me which COM port I need to tell RS Logix to look at. Does that make sense? Usually it finds it okay, but sometimes it don't. But it'll come up and says, I can't find the device on this COM port, and you know it's plugged in, right? And that would be another option that you would go, yeah, you could, but let's look and see our choices. So yeah, we could do that. We could pick and 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 pick. So we could go to 31 of them, and that's the only one it supports. That's the only one RS Logix supports. I mean,
And by the way, you can reassign the COM port. You can hit on right and go to properties. And if it don't assign the COM port that's within that range, you can force it to take a COM port. And I know some of that didn't make sense, guys. Okay, so we found it. So now we should be able to do what? I think I've already auto detected. It found it successfully. And then we'll come over here. Let's just double check. Configure, auto detect, successful. And now when we look at this is still RSM. Now when we come up here and look and see. And we'll come up here and go to comms and go to who's active. It should show up now. So there he is. So we're okay, right? So if we look at this program right here. Don't like this for some reason, does it? Oh, I don't know what's going on. Sorry. Yeah, it's on the Ethernet connection. I don't like something. I might just continue on because we got this stuff we get through. So I'll try to figure this out when we get on the break, guys. These are the two other instructions that we added that's not covered in the book. And this is available on all your Allen Bradley, all the Allen Bradley PLCs that we have. And we talked about a mask. What does a mask let us do? Strip off what we don't want, right? Y'all understand that? And we talked about this new instruction that called the limit test, which replaces the one that we just looked at, the greater than or equal to. So what this one instruction does, it replaces these two instructions right here. If I get my PLC working, I'll show y'all. I've modified that program to use this instruction instead of the other instruction. So here we set a low limit, we set a high limit, and then we set a test, right? And this is supported by RS Logic. Now we need to get through this. So this is the new instruction that we're going to pick up called the jump instruction. Actually, it's an instruction pair. So some instructions we have, you have to use in pairs. What we do is we have a jump instruction. And the jump instruction, we'll either jump forward, we can make the program jump forward or backwards. So what it's going to do is looking for an instruction called what? Label. That makes sense. And what we do is we assign it a number beginning with Q. So that's just what we use for jump. Q2. And then we assign it a number between 0 and 999. The book says
256, but it is 999. So we could literally have 1,000 jumps. Your label instruction, so your jump instruction is an output instruction. So it can be conditional, right? Or the book says unconditional, but we would probably never use it as an unconditional. So what the book calls an unconditional jump instruction is not an unconditional jump instruction. Because as soon as you say something has to happen before the jump occurs, then that is non-conditional. Non-conditional, we see a non-conditional, but we don't do it. It's put in automatically, and that's when it hits the end. When it hits the end instruction, it automatically goes back to what? To rung 0. Automatically. That's unconditional. No conditions have to be met. When it hits that end, there's nothing in the end instruction. You can't put anything in the end rung, right? You understand that as far as an input. That is an unconditional jump. Every other jump that we're going to run into would be considered a conditional. So the book is not exactly true when they say this is an unconditional jump, and then they come up here and they put a switch in the jump instruction. So as soon as I say that, this is conditional, right? Because to jump, it has to do what? This switch has to be true, right? So we can't deal with unconditional jump. We can deal with there's not really available to us.
Where do we do it? Because unconditional would happen.
Yeah, but you can say after the compare it's unconditional, or you can say after all these buttons are pressed it's unconditional, right? You understand? Right? That would be like saying my motorcycle starts unconditionally, but I have to turn the switch on, right? But as soon as you say, but I have to do this, then it's no longer a conditional jump. We do this in PL. So on a robot program does not loop until you make it loop. So you have to put a jump instruction at your last rung and send it back to a label, and it works the same. So jump instructions have been basically the same in every programming language I ever used. And sometimes in true computer programs, if you don't make it loop, it won't what? It won't loop. In PLCs, it automatically loops. It automatically loops. So basically, all our instructions are going to be conditional. Certain conditions have to be met before that jump occurs. And we can decide when it's met. Either we got to push a button, or something's got to be true, or something's got to be false, right? We can use compare instructions. But what you do is you address them as Q2, and this is Allen Bradley. So what you'd have to do is you'd have to, whatever PLC language you'll have to get into, you would have to call, in Siemens they call them function blocks. So they don't call them subroutines, they call them function blocks, but jumps, they call them, well, they do call them jumps to a label. Well, it's very similar even in Siemens. But for every jump instruction, you gotta have a what? You gotta have a label. Jump instructions address can be repeated to cause the program to jump to the same label. So I could call my label Q2:1, and I could jump to 2Q:1 several times, right? You understand? I cannot repeat the label instruction, but I can repeat the jump instruction. Everybody understand that? Looking at the thing.
Every jump has to be the label, have a label. You cannot use the same label address, but you can use the same jump address.
You can use the same jump to the same, you can use the same jump to the same label, right? You understand? That makes sense? Yeah, you can have 1,000 jumps. But every jump you put has to have an address you want to jump to, which is the label. Well, that's not necessarily. You might have 1,000 jumps jumping to the same label. You understand? So we can repeat the jump instruction, but we can't repeat the label instruction. Does that make sense?
Not really, because you said that it can jump to the same label. Is that the equivalent of using the same label?
Well, no. Well, let's just, what we'll do is we'll just use, just,
They're almost there now. Something threw me off.
so I'm up here writing, ladder logic.
So the jump is to
I need to
not
turn.
include the numbers of the block.
Oh, I'm gonna come up here, let's just show you that. So I'm gonna come up here and I'm gonna just say, okay, this is a rung, this is a rung, this is a rung, this is a rung. And down here I put a jump. And it's, okay. And then I say, where do we want to go? Well, I want to go to here. So somewhere down this program right here, I'm gonna start off with an input program and I'm gonna call it what? Here. Right, you understand? So this jump instruction would jump to here, and then it would do whatever I wanted to do. But I could just as well down in here, I could say, I'm gonna say jump to here. Well, what would this one cause? Well, this would cause it would go backwards, right? You understand? But this here is unique. We can't repeat the here, right? I can say jump to here, I can say jump to there, I can say jump to Mars, I can say jump to Jupiter, but I can only have one label called what? Here or Jupiter or whatever, but I can jump to that same level multiple times inside the program.
But jump to a subset. Do another instruction. Come back to the program.
A set of instructions within the same file. So when we come up here and look at our project tree, what we have is when anytime you create a new project, it automatically inserts a program file called what? Ladder 2. And this is true, and Siemens, they call it QB1, because it's a program block is what they call it, QB1. So if I created a project in Siemens, it would automatically create that first program file called QB1. Allen Bradley, when you create a project, it automatically starts a program file called Ladder 2. Right? You understand? Which you can rename. Y'all know y'all can rename Ladder 2, right? How do y'all rename Ladder 2? Just right click on it. Right click on it. Right? So I can come over here and just write over my project tree. Just go to Ladder 2, right click on it, and do what? Rename it. And then I can come up here and I can call it TED. And then as soon as I come up here and enter that, then notice my tab changed to what? TED. It's still Ladder 2. It's still Ladder 2, but now my tab says TED. So we can give it a tab basically that identifies the program. That makes sense? So that's the way we set up a program file. So this program file is, Ladder 2 is automatically made every time you insert. So jumps are going to be within the same program file. But if you notice, I can come over here and right click on here, and we'll talk about this in a minute, and I can say new. And then what I'm going to do is I'm going to make a new program file. It's automatically going to give it what number? 3. And then I can call it, game. And then I come up here and click on that, and it adds another program file, not yet. Now double click on it. Now I have 2 program files. One of them's called what? TED, and one of them's called what? Jane. Well, your jump has to be within a program file, so you can't jump from TED to Jane. You understand that? So you have to jump within this program file. And we'll show you in a minute how to get to Jane. And we can make tons of program files, unless some of your fixed PLCs, like the 1000, I don't forgot how many it gives you, but it gives you a certain number of program files, because remember, it's a little $150 PLC, right? You understand that? And so it's very limited to what it can do. Most of your higher level like the 504 and the 1100, you can create just about as many program files as you want to. It tells you how many. I think it's 256. I think they use 8 bits to identify program files. Well, actually not 256, because you lose program files 0 and 1 because of system files. we lose 0 and 1. So we lose 0 and 1. That's system files used by the PLC. So the first one we get is ladder 2. And then I think we can go to 255, which would give us, 253, 254, program files that we can make. But notice as soon as I set up that new program file, it automatically put an end in there. And this is an unconditional jump. This will always jump us back to run what? 0. Every time it's entered. I can't even put an input device inside that room. Allen Bradley won't let us do that. Siemens don't give you the end. You just know it's what? You just know it's there. They don't put the end instruction out there. So.
Is there a like rung sitting there? There's nothing.
What do you mean?
Like that one has a rung. You're saying there has to be an end rung.
It just don't say.
It's just not there.
It's just not there. But it is there, but it's not there because really it don't make any sense to put it there, right? You understand? If it's unconditional, why put it there? Because it's there just to make the program do what? So you can see it, yeah. Okay, so that everybody see how you can make new program files. I just do what? Right click on it and go to what? New. It automatically goes. You don't have to use 4. You could put in within that 255 range. You could put anything you wanted to in there, right? You understand that? But by default, what it'll do is it'll give you the next available run, right? And then I can come up here and give it a what? A name, and then I come up here. Now what it does, it puts it in the project tree. So if I want to see it and work with it, I just come up here and double click on it, and then it takes me to that next program file, right? And if I want to get rid of it, I can come over here and go to next. And I say, well, I don't need that thing. What can I do with it? I can delete it. It says, are you sure? And now next is gone. So we can add them or we can do what? Delete them. But by default, you get ladder 2. Every time you create a new project, you get what? Ladder 2. Are we okay? And now on Allen Bradley, Siemens call them function blocks. So you do what? You just complete a new what? You create what's a new function block. It pops up the same, basically the same way. Except it don't on Siemens, it don't pop up on a tab. It pops over in your project tree, and you'd have to go out now. You have to come over here. You have to remember, I have to get through my train of thought, right? We have to do what? We would have to click on the Siemens. We'd have to click on which function block we wanted to play around with. I like the Allen Bradley in that once you bring them up, you can just do what? It puts that tab down there, and you can just go between the function blocks. Between the program files real easy. Okay, guys, 5-minute break.
5 or 1?
Lunch is at 12.
Man, you must be hungry. I am hungry.
I think this is actually early for a 5-minute break. I think. Let's go ahead and go. Everybody okay on the jump? It's actually jump the label instruction pair, right? You understand? So what does that mean?
Did I get what?
To jump the label instruction pair. What does that mean? You can't have a jump without a what? A label.
Well, you can't have an unconditional jump or both.
You can't have a jump without a label. Right. Everybody understand that?
Yeah, I'm sorry.
Used to make PLC skips over rungs, always used in pairs. Every jump output instruction must have an associated label input instruction. Uses address Q2:0 to Q2:999. Textbook 255. The label instruction that a jump sends the program to must have the same address, right? You understand? Yes or no? Jump instructions can be repeated to cause the program to jump to the same label. program jumps can be forward or backwards. We all understand that. Unconditional jumps always skip over sections of programs without meeting a predetermined condition. Figure in the textbook and on the next slide demonstrates an unconditional jump is wrong. Automatically inserts into PLC machine language for the end instruction. We've already learned that, right? Seldom, if ever, used. Maybe used. There's only one reason I can figure why you'd use an unconditional jump. And that's to skip over sections of a program that you're working on. You understand what that means? So you can use an unconditional jump. So an unconditional jump means you have nothing between the L1 and the jump instruction. As soon as you put something between L1 and the jump instruction, that is a conditional jump. Because a condition has to be met, right? You understand, before the jump occurs. So the book's a little bit wrong on this. We do have two types of jumps, and I can do an unconditional jump. But the only reason if I put a unconditional jump, it would always jump over those instructions. So if I'm working on a section of my program, but I have to keep uploading it or keep using it, then I could put an unconditional jump and I could jump over that section, right, all the time until I get ready to use it. And then I can add it, and if it don't do what I need it, what I can do, I can put the jump back in.
Well, I understand working on a program, or you have a program here, maybe retooling for another part or something like that, and you don't have to use that process, so you can jump around that.
You could jump around it, or without changing it, right? But usually what you would do, if you were planning on going to it maybe permanently or not using it every once in a while, then you could do that. And that's what we was talking about. While you're modifying our section, you wanted to always jump over. But what we mean by an unconditional jump, it means there's nothing between what? L1 and the jump instruction. That would be a true unconditional jump. If I put something in that rung, a switch then a condition has to be met before the jump occurs. Y'all understand that? So the book's a little wrong. Seldom, if ever used, maybe used to skip over sections, But usually what they would do there, if they were going to do it all the time, is they would put a push button or a switch or something, and they'd flip it in one direction and it would run this program. If they'd flip it in the other direction, it would run the other program. And that way you wouldn't have to do what? So if you made it a conditional jump, then you could select which section of the program you ran.
So this is contradictory to what you're saying. This, I've got it.
This is contradictory.
Because there is something wrong before.
If I have to do this, that's a condition. So for this jump to occur, I have to close that input. You understand? So a condition has to be met. An unconditional jump, it says unconditional, which means what? So if you flip a switch, you just specified a condition. So the guy
I'm just talking about that one rung. So if that were not there, then it would truly be an unconditional switch. The switch were not.
Yeah, if I was to come over here and do this, that would be an unconditional jump. So now what would happen? Every time it hit that rung, it would jump to this label. Every time. And that's, yeah, nothing has to occur. From what I know about programming, and if you look in the manual for the Allen Bradley PLCs, it does not say anything about an unconditional jump. All it says is to jump. It says to jump. I put this instruction where I want to jump to. I put a label. So the jump is an input instruction. The jump is a what? An output instruction. The label is a what? And you can't put an input instruction without having a output. So what we have to do is we come up here and use one of our internal relays. And we got a ton of them, right? Especially with the 1000s and stuff like that, we got a ton of internal relays. We can't have an input instruction on the left. Now I can have an output instruction without an input instruction, but I cannot have an input instruction without a what? Without output instruction.
But what we do is we do what? We don't sacrifice one of our true outputs because it would be silly anyway. So what we do is we use an internal output. So here what they use is the B3, 0/0, right? Everybody understand that? So you can't have an input instruction on the left without having something on the what? On the right. You got to have an output instruction for every input, at least one.
It's jumping over rung 2. And it's
If
going
that-
to
if-
6 to 3.
If that switch is closed.
Okay.
So as soon as I say if,
Yeah.
right to
So
understand.
why would you want something like that? Tell me again, why would you need that sort of?
Test out a program.
Well, not only to test out of a program, but to skip over a section of a program. So like James was talking about.
Okay.
So I'm running 2 different devices. And I run this one every once in a while, and I run this one every once in a while, and I run this one every once in a while. So what I could do is I could put a switch over there. And what could I do? When I close this switch, it executes this section and skips over the other section. And when I open the switch, it does this section and skips over the other section. So I might have 2, I might be loading boxes, and one of them it holds 6 and the other one holds 12. Right, you understand? So what I could do now is I could go ahead and put the ladder, the rungs that load the 6, right? You understand? I might have even a different counter and stuff like that, and then I could put another set of rungs that load the 12. And all I have on a button is a switch that says 6 and 12, and all the person has to do now is do what? Go from 6 to 12. And that way we could have sections of the program that I determine if they run or if they don't, right? That makes sense. So all they're doing here is just demonstrating it. If I close switch 1/0 or whatever's out there, the push button or whatever we have. Right? When we say a switch, it don't make any difference. You know this could be coming from any device, right? You understand? That generates a 1 or a 0. A 1 would indicate that it's true, and a 0 would indicate it's false. And then I either put an examine it closed or examine it open to determine what I'm looking for, right? You understand that? So this could be a sensor out there that senses a certain size thing coming through there. And if it's so big, it's going to send it this way. If it's not big, it's not a certain size, it would send it another way. Well, I could use that situation to either send it down belt 3 or send it down belt 4, depending on its height, right? Or depending on its width or whatever we're doing. So, of course, in our program, we're using switches, or we're using push buttons, or we're using selector switches. That's what we use. But you have to understand, these guys could also be a sensor, right? To understand that senses things and gives us a true or a false of what it senses true or what it senses false. Could be a reed switch, could be a Hall effect, it could be a inductive sensor, it could be an optical sensor, it could be any type of sensor that's sensing different things. So if it's a certain height, I could have like a through the beam sensor, which we talked about in PLC1, right? Through the beam sensor, and if it trips that, then it would do this. If it don't trip it, then it would do that. And that's what the power of the jump instruction is. So using these jump instructions, we can deliberately make it do what? Skip over sections skip over a section of a program until what we're looking for is true. So we could do AND logic, we could do OR logic, we could do compares, we could do the results of a math operation, right? We could skip over it as long as so we could skip
So
over.
it doesn't have to be done with a physical switch.
It doesn't have to be done with a
the
switch,
counter.
and that's why we went over
math.
the first class. That's why we went over there to what? We went over to the PLC lab and let you, the mechatronics lab, and actually see all these sensors, right? You understand? So how many push buttons do they have? They have on the automated system, you hit one start button basically, and then all these sensors does what? It decides if it does this or does that or jumps over this or jumps over that. It's all these inputs that need it. Unfortunately, we can't simulate it. So that's why on this box I put an inductive sensor on it. So what we have to do is we have to make, when we put a jump, we're gonna have to give it an address. Now it's gonna be a Q, it's gonna be a Q2, right? And then I'm gonna have to give it a number. And then my label is gonna have to have the what? The same name or the same address, right? Does that make sense? And that's the way we can combine jumps. I could jump within a jump, by the way. As long as I give it a what? A different label. Does that make sense? So we could jump within jump.
Different parts, different parts of the program.
Yeah, I mean, we can jump within jumps. It's up to you when you're sitting there trying to figure out, well, okay, well, heck, I'm within a jump, but I need to jump over this. So we can put jumps within jumps. It's just that each jump, if we're going to put jumps within jumps, and each jump would have to have its unique label, right? You understand that?
So what would you do? How would you do that? Would you put a branch down under it and do, like?
No, I would just come in here and put a rung, I'd put a rung, and then I would put a jump, and then I would jump to the label that I want to do it, right? Does that make sense? Yes or no? Huh? Well, we'd have to do it with something like a Logic Pro. Unfortunately, I got so many wires up here, I can't get to my mouse. So I think we've got this program right here in Logic Pro. I think this is figure. What's this figure?
What you're saying is like, pretend if it were that line, sort of the line that you have down in the mechatronics lab, and it gets to a certain point, jump. But you also want something down the line to jump when that is true. Like say if it's
Yeah, so we can put jumps. We can put jumps within jumps. What's the figure number for this? So right now so when we come up here and run this, oops. What do we have to do here? We have to close. Oh, we have to go run. So right now we have this energized. It's doing what? Jumping over this, right? You understand that, and then go into the label. So you see, let's do switch 1 first. Well, even though I'm switching switch 1, you notice that output 2:2 is not doing 1. It's not turning on. Why? Because it's jumping over it, right? I'm gonna come up here and open up switch 0, and I'm gonna close switch 1, and now it turns it on. Now what you got to remember, so what I'm gonna do is I'm gonna come up here and I'm gonna turn switch 0 off. Now notice what happens to the output. The output's gonna stay energized no matter what, because we're not scanning, we're jumping over that, updating the output, right? You understand? So what I'm trying to tell you, if you turn on an output and then you jump over it, yeah, then switch 1 is not going to do anything. So I'm going to come over here. So switch 1 is not even, it's still scanning the inputs, but notice the output is basically latched on because we're not updating that output anymore because we're doing what? We're jumping over it. That makes sense. So this is, you got a lot of people think that if I take the jump away, if I jump over it, then the output is going to go false. But no, it's going to keep whatever state you had before you started doing what? Before you started jumping over it.
So do it again from the beginning, or how did you?
First of all, what we did is we come over here and, what determines whether I'm jumping or not would be switch 0. So right now, we're not jumping over it, right? You understand? So when I come over here and close switch 1, okay. I'm sorry. When I close switch 1, it turns on the green light, which is outside of the, let's do the green, let's make it green, since they call it green. And they call this one what? Red. So we'll make this in red. So now it makes sense. So right now, when I close switch 1, the green is outside the jump, so the green comes on, right? You understand? And then the red is inside the jump, right? So it's turned on, right? You understand? Because right now I don't have the jump what? Enabled, right? You understand? Okay. Right. So what I'm going to do is I'm going to come over here and tell it to jump over it, so I'm going to close 0. Now I'm going to come over here and activate switch 1. And you notice the green light turns off and on because it's what? It's outside the jump. But this guy right here don't do anything anymore. So even though we're scanning inputs, we still scan inputs, but what it's not doing, it's not updating the outputs, right? Move on one. So this light is on all the time. Why is it on all the time? Because I'm jumping over it. I can't turn it off because I'm jumping over it. Right.
So when it jumps over it, the end becomes true as well. Is that what it's going back to the cycle?
Well, the end is always true. So this is our unconditional jump. This is our unconditional jump right here. So if it ever hits that end, it's going to go back to rung 0. Period.
Okay, and that's why the red stays on because it's now
we're jumping over it. So so if I come over here and so right now I'm going to take off the jump and see now I'm controlling both of them. Okay. Now I can turn, right? You understand that? So let's turn it off and now we'll jump over it. Okay. So now it's off. Now I'm going to hit switch 1 again. And now I'm still turning off. I'm still doing the first one, but I'm not doing anything within the wall. Within the jump. And what we were talking about a while ago is I could jump within a jump. So what I can do is I can come up here and insert a rung right there. Let's insert a rung right here. And then, so this is within the jump, right? You understand? So what I could do here is I could come in here and set up another switch. And then I could put another jump instruction. Now, where are the jump instructions at? Well, they're here in the program control. So this is where your jump instruction's at. And then I can come up here and I can put a jump instruction. What I have to do here is I have to give it a what? Yeah, Q2 colon what? 2. Now I put a jump instruction, so what does that have to mean now? Yeah, I've got to have a label instruction, right? So we'll assign this to input to and then what I'm going to have to do here is I'm going to have to put a label instruction. And of course, the label's an input. And then I have to give it a what? Colon 2, right? You understand?
You could have used 0, right? But it didn't.
No, because we're doing a jump within a jump. If I would have put a 0, then this jump would have been nothing. This jump has no label. It has nowhere to go to. So for every jump you put, there's got to be an associated label.
I mean, initially, you could have used 0.
Oh, okay, yeah.
Okay.
It's just that they used 1 right here, so we did what? So I know what you're talking about now. And now since I've got an input instruction, what do I have to have now? I gotta have some type of output instruction. So what we'd use is we'd use one of our bit files, right? Oops. And I think we could probably tell you the truth. I think we probably could use the same one because we're not doing anything. Yeah. So now what we have is we have a jump within a what? Within a jump. right? So that means if I come over here, I could activate this jump. When this one's false, I could activate this jump, right? You understand? And if I do that, then neither jump would be activated. So this would be an example of a what? Jump within a jump. I could have put the jump down here and jump backwards, and what you have to understand is that we can either jump what? Forward or backwards.
But whatever address you jump to, whatever label, it will eliminate whatever is in between the jump instruction.
Well,
and
it
the
will,
label.
it will not update
Not
the outputs.
activated. Okay.
It still scans the inputs. The inputs are still scanned.
So at this point, even that jump will be inactive, that second jump in the new jump, that jump in the jump.
Yeah, probably.
You have to activate it.
Yeah. So right now we're in run, right? So right now we're jumping over everything, so I can do switch 2. See, and nothing happens, right? You see that? And then I come over here and take switch 1, switch 0. Now it's not jumping, right? You understand? And now I can come over here and flip this switch, and this works, right? I'm sorry. I'm kind of confused. But now if I did this, what would it do? It should be still able to turn on the green light. No, I'm jumping over. Oh, I have this guy enabled. So this is jumping to this label right here. So both of my jumps are jumping over the same instruction. So we'd have to, y'all see what I'm talking about?
Yeah.
So what we have now is this jump is disabled, but this one is enabled. So I can't change the status of the light, right? If I come over here and take this jump off, I still can't change the status of, which one did I have jumped? So this is the first jump, right? Okay. And I can't update the status of the light. And then here's the second jump. And now it's true, and I can't update the status of the light. But all this is doing is just generating how we could put a jump within a wall, within a jump. Everybody okay? And I can't get my PLC to work over here right now. So here's what they're demonstrating a conditional jump. So here they're saying, okay, if my counter's equal to what? 5, it's going to jump to Q2 label 1, which would be what? Q2 label 1. Right, let's have that. Okay. So it would skip over this guy. If this guy is true, is greater than 7, right? It's going to do what? Jump to Q2 2, which would be this guy right here. It would be this guy right here, right? Everybody see that? So here, these are definitely conditional jumps. Here they're using, so the book says, to get a conditional jump, you have to use compare instruction, but that's not true. If you put anything over here on the input, it would be considered a conditional jump, right?
Yeah.
Everybody okay? This is another instruction that they've added. It's called the master control reset. It does not replace the required external e-stop circuit. So an e-stop circuit has to be hardwired. I can show you all type of regulations. It cannot be done by a computer. It cannot be software. You understand why? Because you saw a while ago, we have problems with these computers locking up every once in a while. We have to turn them off and reset and do all kind of weird stuff. Used in conjunction with a hardware, we can use this in conjunction with a hardware e-stop circuit. Always used in pairs, so we have an MCR output instruction. The first instruction is conditional, while the second instruction run must be unconditional. Remote control devices between L1 and MCR output instruction. Disables all non-retentive outputs between the pair when the first MCR is false. Disables non-retentive outputs when the first input runs. Say that twice. Inputs are still scanned and updated. So usually when we hit an E-stop, what are we gonna disable? We're gonna disable inputs or we're gonna disable outputs?
Say that again?
Outputs can hurt people. Inputs can, right? You understand? So normally what we do is we disable your outputs, but we got problems in that I've got a crane up there with a big magnet on it holding 2 tons of steel, and I turn that output off and it drops that steel. Right? You understand that? So this is why we have retentive contacts. By the way, if we're going to do that, we're not going to do that with a PLC. We're going to do that with a relay called a latching relay. I think I showed you that, right? So if we want something to stay energized when I kill the power to my PLC or something happens to my PLC, then we're going to latch that sucker outside of the PLC. Does that make sense? So we'd use what we call a latching relay. So a latching relay, if you latch it, you have 2 coils on a latching relay. One of them's called latch, one of them's called unlatch. If you latch that sucker, if you lose power to the latch, that relay stays, those contacts stay closed or open, depending on whether they're normally closed or normally contact. So if I've got something that's desperate about staying on, we're not going to do it with a program, right? Because programs can make mistakes, yeah. We can make mistakes.
So what do you do about that 2 tons of steel that?
You use a latch and relay. You can latch it with your PLC and you can unlatch it with your PLC program. But what you do is you use a latch and relay. So that way if something happens to the power on your PLC, because if I'm gonna hit a master reset, I'm gonna kill all my outputs on my PLC. That's what I want to do. I want to kill all the outputs. But if I've got something external that is desperate like that, then we won't use the PLC, we'll use a latch and relay. We could use the PLC to latch it, and we can use the PLC unlatch it, but when I kill power to my PLC, I'll kill those outputs, right? The MCR does not require an address. Additional MCR pairs cannot be put within an MCR pair. So you cannot, unlike jumps, you cannot have an MCR within an MCR. Right? Use to stop operation of control systems during high voltage output. This is what the book says. We have all types of reasons why we would use an E-stop. An E-stop is not a normal stop. Everybody understand that? I've seen people do that. They'll use an E-stop to stop things just instead of using the stop button. An E-stop is an emergency stop. If you ever did that on a robot and that robot was in motion, that sucker stops. And so what you got is you got all this kinetic energy moving, right? You got these motors moving and all kind of stuff, and you slam on brakes and all kind of stuff, and you can cause all types of problems. So the robot has either a hold button or a stop button. If you hit that, the robot decelerates. It does it real fast, but that way it won't sling its load and everything all over the place. So we don't use the E-stop unless we have an emergency. Everybody understand that? Usually connected to the power switch. This is what we got to understand. Retentive or latched output are not disabled. The book does not tell you that. Note that any device that must stay energized during an E-stop should be what? Hardwired. And we've got a program out there we'll run. But let me show y'all an actual E-stop circuit. So this is a basic E-stop circuit right here. And this is hardwired. This is electrical. This would be out there on a panel somewhere. So we have an E-stop, and basically it's just a standard memory circuit, right? Understand? We use a relay. When I hit my master reset or my master start, and I hit that button, it just comes in. Then my E-stop button, by the way, a couple of things. It cannot be a momentary contact push button. It's got to be, and it's got to latch in the E-stop position. Everybody understand that? So we can't use a push button for an E-stop. So, and it can't be spring returned either. So on an E-stop, you got to deliberately do what? Pull it out. So on this guy right over here, we can see this. So this is an E-stop button. Most of your newer E-stop buttons actually require you to push it. So there's no spring in there. In fact, it's pushed in.
This is that same basic circuit right here, except to reset it on this one, this is a key reset. So instead of having that push button on the master reset, I have to literally come over here. So come over here and pull out on it. So notice what I had to do to get it out. I had to pull it out, right? Now what I have to do to energize this, on these I have to go there and get a key. And I would turn it and it would make that contact up there that's showing the reset. When I come over here and hit it, it does what? It latches into the e-stop. Most of your new e-stop buttons, you can't even do this. Most of them you have to twist them. You have to twist and pull them out. But usually you have to push them in, twist them, and then pull them. So that way you can't accidentally, you have to deliberately pull the e-stop out. And then you have to reset the relay. So I got my key and I opened this up, you can see this master control relay inside here. So this right here is almost exactly what I got up there. Everybody understand that? Then what we would do, we talked about that common while ago, that common. But what I would do, these outputs are sourcing on this example here. So I have this hooked up at sourcing. So this is the 1100 PLC. By the way, you see this done a lot too, where you got this big old line that's, 200 yards long, and you got one e-stop button that's at the very start. Well, usually lines are divided into sections. Each section has a function in that line, and usually every section would have an e-stop button or an e-stop cord. A lot of these big production lines, they have cords hanging from the foot that you have to do what? You have to pull. So this is the standard e-stop circuit right here for the 1100. So here's my, we've got these things hooked up as sourcing, right? You understand? So this is the Allen Bradley, the 1100. This would be my e-stop contact right here, controlled by what? That relay. This would be my power supply for my output. So what happens when I hit that e-stop button, what does it do to all my outputs? Kills all the power to every one of them. So now my outputs can't output anything. That makes sense. Are you okay?
Is that what that diagram was?
Yeah, this diagram right here, this is E, this is DS. I call it DS. Most people call it MCR, but the problem is why I didn't call it MCR, for a master control relay.
Oh, I see.
Yeah, for a master control relay. They usually call it MCR. I didn't want to call it MCR because that's what the book calls their master control reset, right? Are we okay? So this would just allow us to put multiple e-stop buttons. By the way, I couldn't find the ANSI signal. This is actually, I'm sorry, the ANSI signal. This is actually the ISO signal for e-stop buttons. The international standards for e-stop buttons. And notice it's got this mushroom head on it. So these are not really, some of them are really extenuated. You don't have a guard, you can't have a guard around it, right? You understand that? So you can't have somebody have to pick up a guard to hit an e-stop. So these things got to be out. They got to be red. Some of them are lit, right? Some of them are lit. So it uses a double pole contact in there. One of them powers the light and one of them breaks the circuit. So these are all lit. So when it's out, it's actually lit, right? You understand? But now what they have to do is the e-stop button, the actual button itself has to be red, and it's got to be against a yellow background. So that's the rules now. Of course, in the older buttons like this, you won't see it against the yellow background. All your new ones, you'll see it against the wall, the yellow background. Usually just a little ring or something. Might have arrows on it that tells you which way you need to turn it to unlock it. Some of them actually dislabel the outputs too. I mean the inputs too. If I was going to disable the inputs, I would just put another contact in what series with the COM on your input. It all depends on where you work at. Do they want to kill all the inputs coming into the PLC or kill all the outputs? Normally what we do is kill all the outputs because the outputs are the ones that can do what? They're the ones that can kill you.
you're saying you could kill the inputs as well?
Sure, I could come over here.
Why would,
So what we, first of all, we'd have to do is establish a common, right? So if I use, so notice I have, this is the DC power supply, but I could also use another DC power supply, and I could use this one, in fact. So what I'd have to do is, I would come over here and, I would take this right here and I would hook it to these two commons, and that's the way I set up syncing. But what I would do is I would just put another ES contact right there. If I put an ES contact between my common, right, my input common, then I could kill my inputs coming into the PLC. It doesn't mean you're killing power going to your to the inputs themselves. You're just killing those inputs coming into your PLC. That makes sense. Or I could come up here and use an external power supply, which is what I'd use down here. Could be the same power supply running your inputs that's doing what? Running your outputs, right? That makes sense. So I could come up here and I could tap off right here, and then I could come up here and put another ES contact, and then I would come over here and come in like that. That makes sense. And of course, then I would take this, and then this would run up to my input switches or whatever I'm using. That would be my common for my input switches, right? And on here, I would take this guy and run it to the common on my output device. So you could see normally you don't have a power supply for your inputs, and in your outputs you have an external power supply that you use for what? For both of them, even though you could. You could have two power supplies, run one in your inputs and one run in your outputs. You could have two power supplies, which you might run into that too. All you got to do is establish a common and then use the other side. So I know it's almost time to lunch. So let's bring up this. And what I've done on this one, I've modified the one that, and I think this is a Logic Pro program right here. So what's that figure number in the book? Let's see, MCR. Yeah, here's MCR right here. 1111. So these are the two retentive contacts that we have available. One is called latched and one is called unlatched. And notice they get the same output number because that's what they are. They're the same output. So when I come over here, I'm going to download this. So this is a little different than the one in the book because I wanted to show you about these non-retentive contacts. So notice on my latch, so I'm using my latch, I'm using push button what? 1-3. So what I'm going to do is I'm going to come over here and I'm just going to hit it. Oh, MCR. I got to make the MC, so notice my outputs don't change. So what we do is we have to make this run false up here. I'm sorry, we make it false to skip over, and then I'm going to use switch 0. Now my MCR is true. And notice what I do when I hit my latch. That output comes on and does what? Stays on. Even though this run here is not true anymore, right? I understand that. So it did what? Stay latched, right? You understand that? Now, how do I turn that thing off? I'm going to hit switch 4. These are momentary. And then it unlatched. So this did what? This does what to it? Latches it. And this does what? Unlatch it.
why does it highlight the other?
It's the same. Yeah, because it's technically the same. Technically, it's the same relay. Yeah, if I looked at my big relay over here, I've got two sets of coils called latch, and I got one called unlatch, but it's controlling the same. It's controlling the same outputs, right? Y'all understand that? Yeah. So if you put a latch, as soon as you put you have to assign the unlatch to the same coil number. So when the guy says you cannot repeat outputs, That's not exactly true. Because I could use jumps to the same label, right? You understand? So that would be the same jump with the same address. So I could use that multiple times. Well, here's one situation where we assign the latch and the unlatch because technically this is the same relay, right? So now I've got them enabled. And let's go ahead and we'll do switch 1, which turns on this output. And then we have another. And what I'm going to do is I'm going to come over here and turn off my NCR. Well, notice what happened. Even though this input is true, this output turned what? Off. This guy did what? Because it is a latch unlatch. So this is what we would call a retentive output. Right? You understand? And this is the only real retentive output I know of is when we use this latch and unlatch. And I can come over here all day long and unlatch it. And now I'm going to come over here and try to unlatch it with switch 4, and it's not going to do anything. And why I need unlatching? Because that MCR causes it to skip over updating your output. So what we would do is we would use this in conjunction with a e-stop. So we might come in and have the e-stop. We might have a contact on that e-stop, that hardwired e-stop circuit that would be normally closed, right? You understand? And then when I hit that e-stop button, not only would it kill the power to my outputs, it would also kill the outputs themselves, right? You understand? Except for the retentive contacts. And that's the problem we have. So right now, this output right here would be turned on, and this output right here would be turned off, right? I mean, I'm sorry, it would stay where it's at. So normally, if we're going to use something that cannot be turned off, then we will use a latching relay outside of the PLC, right? Now we could use this right here to turn them off and latch them and unlatch it, right? You understand that? But once it's latched and power fails to my PLC or something like that, I wouldn't want my crane to do what? Drop them out, release a brake somewhere on a motor. So I've got a brake on a motor. Of course, it's stupid to put a brake on a motor that has to be powered to turn the brake on. Most of the time, the best way to do brakes, we got our robots over there from Amtech, which they made 2 of our robot sales. They hooked the directional control valve, so if you kill power to the robot, the dang thing's open. Which is dangerous. All we did was just change the piping around, because what you wanted to do, if something happens, you want that gripper to do what? Either stay closed or closed. We don't want it to open, because if it opens, what would it do? It would drop what it's holding. So we just swap the pipes around. So this is a company that makes robots that put them backwards. So yeah, we noticed that right off the bat. We were over there on the big ABB robot. It makes so much noise that when we're lecturing, we go over and turn it off. And we went over right after we got it, and we turned it off, and it was holding something. What it did? It dropped it. But all we had to do was just swap the pipe around. It wasn't hard to do. The KUKA robot uses latching relays. You latch it, right, and then if power fails, it uses the latching relay inside the robot. It didn't have that problem. So this is through with this chapter. I was trying to get through, and I can't communicate with my PLC to show y'all some. I wanted to hook this up and actually run that for you. I can't get it to communicate with it right now. Next thing we're going to look at, guys, is we're going to look at subroutines. Anybody know what a subroutine is?
Basically that file where you need
And what we find out is that we call it structured programming. The longer a program gets, the harder it is to manage. I mean, it's really hard to manage. So I'll show y'all this real quick. So these are the actual programs that's, yeah, we're going to let that.
Meet over there? Or come back here?
Now we're going to meet down there. Not on that right now. Go, hold on. I still have 5 minutes. So this is the programs that run the Festo line. And notice over here on my program tree, I have ladder 2, I have ladder 3, I have ladder 4, I have ladder 5, I have ladder 6. Okay. And we can open up each one of these. And so when I go back to ladder 2, which they consider to be the main program. So notice I get all these tabs right here now, right? So here's the original program. But right off the bat, I see an instruction called what?
Jump to
Subroutine. And now it's going to jump to subroutine U4, which means program file 4, which means this would be 2, 3, 4. So this would be the one it goes to.
So what this does is this would automatically take care of what it needs to do to handle the what? An e-stop situation. Okay. And then what would it do if I go back to my original one? It says jump to subroutine what? Now this is conditional. This is a conditional JSR, right? You understand that? This right here is an unconditional. So that means every time it hits run 1, it's going to go to subroutine file 6, right? And this would be file 6. So this would be 2, 3, 4, 5, 6. Now what does this subroutine handle? This handles the what? The stop. So if I hit the stop button on my PLC, this subroutine handles that. So if I was having problems with my stop function, I wouldn't have to go in there in this big old long PLC program and find that stop program. I would have to just do what? Go to the file, and then I could play around with this. Right? You understand? So what we usually end up with, if we looked at ladder 2, it's nothing but jumping to subroutines. Jump to 4, 6, 5, and then it takes care of some other business. Okay. So what we have is we have what we call a main loop, which basically just calls subroutines. Now what's so cool is if I came over here and looked at this e-stop. So I have an e-stop on every one of them. I have a stop on every one of them. I have a blinking on every one of them. So instead of me trying to rewrite this every time, right? So what I can do is I can come over here to actually another testing station, like the handling station, or processing. That's got 2 files. And I notice, what does it do? It's got origin. And if I look at this one, what do you notice? Jump E4, jump E6, jump E5, everything's exactly the same. So what I'm saying is I've got all these different modules, but how they handle each stop is what? The same. How they handle this is the same. How they handle this is the same. So instead of me having to rewrite all those little programs, I write them as modules, right? You understand? And then I can import them from a library into my program, and I don't have to rewrite them. So the only thing that changes between each one of these is this thing called auto. This is the program that actually handles that station. Does that make sense? So this is the only, so I could go to every station, and those other 4 modules would be, how do you handle a stop? Well, they all handle a stop the same way. How do you handle e-stop? Well, they all handle e-stop the same way, right? How do you make the lights on the front of the panel blink when something's going on? Well, they all do it the same way. So instead of me having to go in there and write that sucker what? Every time, we can do what? We can put them in a library and do what? Then import them in as a different file, which makes it really, really sick. And plus, the program is a lot harder I'm having problems with my e-stop. Well, instead of me trying to find that e-stop program inside a program that's 1,000 runs long, I can write it as a what?
So,
I can write it as a subroutine, and then I can go and do that. You learn right off the bat, if you get into programming and you get into these robot programs, that's thousands of lines of code, and you're trying to go in there and figure something out, and you don't split that sucker up into modules, you're going to be crying. Oh, you're going to have a bad day. So if we looked at, I should have showed y'all the, next time, if you're in another one of my classes, let me show y'all the robot that's running the Amatro line over there. It's nothing but what? So, well, it's subroutines. Got one main loop. And we had problems. We had to reteach a point. Right? So instead of me trying to find that point inside a line of code, 200 lines, I went to the subroutine and I did what? And then I could retaught the point in there too. So yeah, subroutine, structured programming. If you got people that write thousands of lines of code and they don't use a structured program, if they don't take that big program and split it up into modules, you're going to learn a new language. You'll cuss those people out a lot. And that's true. Unstructured programming is awful. Okay, guys. See y'all down at the lab. I need to try to get my bill. And I got a list, by the way. Y'all remind me, I got a list of the labs that we're working on. I need to give that out to y'all so y'all know how y'all standing in the class. I got it under my wheelchair in fact. Here we go up here. I don't know why they put them on the desk when I got this thing. It always surprises me. Okay, guy, where did you go?